Okay, so here we go. Section 10.1, parametric equations and calculus. Okay. If x and y are both differentiable functions of t, if x and y are both differentiable functions of t, and if dx dt doesn't equal 0, then what's dy dx equal? You guys gave me this just a minute ago. dy dt over dx dt, right? And that's because if I went through the process of multiplying by the reciprocal, what would happen to the dt's?
Cancel.
They would cancel out. If y prime equals dy dx, okay, so we're going to give dy dx a different name. We're going to call it y prime. And is also a differentiable function of t. Okay, so notice y prime is the dy dx. Okay, that's what we're calling it. Then a differentiable function of t, sorry. If y prime equals dy dx and is also a differentiable function of t, then the second derivative equals that, does it not? The derivative with respect to x of y prime, right? That's just another way of writing it. It's the derivative of dy dx. Okay, so what it really is the derivative of y prime dt over dx dt.
Where did the dx under the d go?
It's going here with the dt. Wait, let me see if I'm saying that right. I want the derivative. That's the same as the derivative of y prime dt over yes, it's here. I have to. It's here.
Okay.
Okay, and here's why. Okay, so to get the derivative of y prime is it is dy dx, but it's in terms of t,
Okay.
right? It has t's in it. So I've got to take, if I want the derivative of y prime, I've got to take the derivative of y prime with respect to t. But it is with respect to x, so I have to take care of, to get this dx, I have to do that dx dt. Okay? All right. So then what I'm going to end up with is d dt, right? I'll pull this dt over here with this d, and then y prime was dy dx. I pulled this dt out here with this d, so I have d dt, and then y prime is dy dx all over dx dt. I promise this is going to make more sense when we do an actual problem. And then I'm going to write it in words for you too. Okay, so in other words, yeah, in actual words, to get that second derivative, take the derivative of dy dx and divide it by dx dt. Okay, so in order to take a second derivative, we got to take a first derivative, right? So we're going to take the first derivative of my parametric. And then to get the second derivative of the whole thing, I'm going to take the derivative of what I got, and I'm going to put it over dx dt. So let's do an example. Given x equals 2 square root of t and y equals 3t squared minus 2t, find dy dx, or find the first and second derivatives. Okay, so dy dx, you guys already told me is equal to what? dy dt over dx dt, right? So what is dy dt? 6t minus 2. And 2 square root of t, remember, is the same as 2t to the 1/2. So t to the negative 1/2. So if I know I'm going to have to take the second derivative of this, so I would clean that up a little bit, right? How do you guys want to clean that up?
T to the 1/2.
I could make it t to the 1/2 to the top. What did you say, Skylar? Did you say the same thing? Okay. So this is 6t minus 2 times t to the 1/2. I can move that to the top.
You get factor of 3, or sorry, 2.
Yeah, I would distribute it back, right? Instead of factoring out more, because I know I'm going to have to take the derivative of that. So let's avoid product rule if we can, or quotient rule, or whatever. So then this is 6t to the 3/2 minus 2t to the 1/2, right? Anybody with me there on the first derivative? Yeah? Okay, so second derivative says to take the derivative with respect to t of dy dx and put that over dx dt.
Is that the same dx/dt we already found?
It is. Yes, it is. Okay, so what is the derivative of dy dx? Go back over here. That's going to be what? 9 t to the 1/2, right? I have to take the 3/2 down in front and multiply, and 3/2 times 6 would give me 9. So 9t to the 1/2 minus t to the negative 1/2. And then all of that's going to go over dx dt, which I found already, right? And it was t to the negative 1/2.
Where's the 9?
3/2 times 6.
Oh,
Okay, and then again, you probably want to clean it up so it looks a little nicer. So I have 9t to the 1/2 minus t to the negative 1/2 times t to the 1/2. I can move that up.
For Sanders, where did you get the t to the negative 1/2?
That is dx dt.
Okay. Oh.
Okay, and then that's going to give me t to the 1/2 times t to the 1/2 is just t. And then t to the negative 1/2 times t to the 1/2 is t to the 0, which is 1.
do what? You
And do you guys see how this works? Like this is like d dt, dy dx, and then if I multiply by the reciprocal dt dx. So these go away, so it's d dy that we talked about right up there. And then dx squared right there. Anyway.
Oh, is that why it's dy's?
Is that what it
Is
is?
that why it's d squared y dx squared?
Yeah. Nice observation, Natalie. I learn something every year. It's good stuff.
That's why the T's are in the spots.
Okay. So let's do a couple more example problems, or we'll do another kind of problem, and then we'll look at arc length. What's my time? Okay. All right, so let's look at this example. Find all points of horizontal and vertical tangency given by the parametric equations x equals t squared plus t and y equals t squared minus 3t plus 5. Find all points of horizontal and vertical tangency Trying to get you a good picture of it. Okay, I'll start with this one. So here is this particular set of parametric equations, right? X is defined to be t squared plus t, y is t squared minus 3t plus 5, okay? So if I look at the graph in this window, I'm trying to find out where my points of vertical tangency are and horizontal tangency are. So I think this one is pretty easy to see, this horizontal tangent right here, okay? But maybe not so easy to see the vertical tangent. So let me change my window here, and I just know because I did this already. But if I change my window a little bit, what you see is this is really doing this. It's going, let me go zoom 0.
I zoom fit. That's what I
Yeah.
did. That was pretty good.
So there's a graph where you can see, here's your horizontal tangent that I'm looking for, right? And this vertical tangent, do you see it somewhere in there? Okay, so that's what I'm looking for, so that you have a visual of what you're looking for. You are looking for the points on that graph where I have a horizontal tangent and where I have a vertical tangent, okay? What's gonna determine if I have a horizontal tangent? Where what? Okay, where the derivative is equal to 0, right? That's where I have horizontal tangents. Where do I have vertical tangents? Where the derivative is undefined, right? Or something over 0. So the nice thing about parametrics is, with parametrics, it comes out in a rational expression, right? So what represents the numerator?
Horizontal.
dy dt. So if dy dt is equal to 0, then I know I have a horizontal tangent. And if dx dt is equal to 0, then I have a vertical tangent. Now I do have to be careful because they could both be 0. If they're both 0, then I don't have vertical or horizontal tangent there. I have a hole in the graph, right? So if I'm looking for a horizontal tangent, I want to know where dy dt is equal to 0, but dx dt isn't. And then similarly for vertical tangent. Okay, so here we go. Horizontal tangent. Implies that dy dt is equal to 0. And dx dt is not equal to 0, right? And a vertical tangent dx dt equals 0, dy dt doesn't. Okay, so let's figure out what dy dt is. And what will dy dt be?
2t plus minus
2t minus 3. And I want to know where dy dt is equal to 0. So that's at t equals 3 halves, right?
That's a horizontal.
Yes, this would imply I have a horizontal tangent. Let's go ahead and figure out what dx dt is and make sure we don't have any 0 over 0s. dx dt is equal to what? 2t plus 1. And that's equal to 0 at where? Negative 1/2, right? So will this value of t that makes dy dt equal 0 make dx dt equal 0? No. Will this value of t that makes dx dt equal 0 make dy dt equal 0? No, so we're good, right? Okay, so what do I need to do now?
Over each other.
Why do you need to do anything else if you already found out the points of tangency?
I haven't found out the points of tangency. So what do I need to do next, Natalie?
You need to plug the x values in.
I don't need to plug x values
The
in.
t
I need
values.
to plug t values in, right? Because I want to know the point, right? I'm looking, there's some point on this graph, some point x of t, y of t, where I get a vertical tangent, and another x of t, y of t, where I get a horizontal tangent. So all I need to do now is take these values of t and substitute them into the original equations.
So you need the second derivative for this.
I don't need the second derivative for this, no. And that's why the title of this is just parametrics and calculus, because we're doing a couple of different things with them.
Well, I just typed in
Okay.
t equals negative 1/2 on my graph and it gave me invalid.
Good. These would be a non-calculator question. But I'm glad that you're doing that. I mean, because we want to be able to do it. We want to be able to pull from our calculator and have a visual of what it is that we're finding. Okay? So I need x of 3/2 and I need y of 3/2, right? So x of 3/2 would be 3/2 squared plus 3/2, which is 9/4 plus 6/4 or 15/4. And y of 3/2 would be 3/2 squared minus 3 times 3/2 plus 5, or 9/4 minus 18/4 plus 20/4. So what's that? 11/4? Therefore, a horizontal tangent occurs at 15/4, 11/4. And then I would just need to do something similar with the t equals negative 1/2, right? So x of negative 1/2 is negative 1/2 squared plus negative 1/2.
Yes.
Negative 1/4. That's x of negative 1/2, but then I also need y of negative 1/2, right? So to get y of negative 1/2, I just have to plug that in. So I have negative 1/2 squared minus 3 times negative 1/2 plus 5, positive 1/4 plus 6/4 plus 20/4. Is that right? 27/4. Therefore, there's a vertical tangent, or vertical tangent occurs at negative 1/4, 27/4. Okay, so just a different kind of problem where I'm having to analyze parametrics. One other thing, and then I'll let you go. Everybody stayed up late for your 4-day weekend, and everybody's tired. I couldn't get my child up this morning to save my life. Okay, so we've done arc length, right? We did arc length. We figured out how to calculate the length of anything we have, basically, right? Of any kind of curve. And how did we do that?
Square root of 1 plus f prime.
Okay, and we did and what did we do with that, Bill?
Well,
We integrated it, right? Why do we have to integrate it? Because we were adding together all those tiny little tangent line segments, right? Okay, so before it became the square root of 1 plus f prime of x, what's the first thing that we wrote?
I squared. No, the distance formula.
It was distance formula, right? It was my distance formula. And the distance formula is the square root of what?
Delta x plus delta y.
It was delta x squared plus delta y squared, right? It was change in x squared plus change in y squared. And then I had to do some fancy footwork to get it to say what I wanted it to say. But the beautiful thing is with parametrics, don't you already have change in x and change in y?
Yes.
You do, right? So this is what we started with whenever we did arc length, is change in x squared plus change in y squared, which is this, right? And then, well, it wasn't totally correct. So we had to do that right there. So arc length of a parametric curve. Nothing that says you can't use L again for arc length. In books, they typically pick something else since we're talking about a different kind of function, but no big deal if you use L for arc length. So what we would be saying here is that S is equal to the integral from A to B of the square root of dx dt squared plus dy dt squared. And what's my variable of integration? dt, right? So the only thing I want to caution you about is if this is dt, A and B have to be what? In terms of t. Very good. Okay, so we'll just jot that down. A and B must be in terms of t. Therefore, you'll see written sometimes the integral, that's just supposed to be an S, not an integral, which is what it turned out like. T sub 1 to T sub 2. Isn't that cool how that kind of works out? I mean, it's the same idea.
I keep looking at my S and thinking it's like a messy integral.
All right, so I have some homework here for you. It's this worksheet.